Hello and welcome back. There's a lot of text on the board, so please don't be overwhelmed. We'll be going over everything nice and slow. So to begin with, I'm just summarizing what we've looked at previously. We defined work. Work got the symbol W. Remember that this integral symbol means area under the curve. So this is the integral from some initial position to some final position using X to keep track of position here of F, the force acting that I'm calculating the work for, times the cosine of the angle between this acting force and the displacement of the object times an infinitesimal displacement. And so this is just the area under the force times the cosine of theta versus displacement graph. So if I have a graph of F cosine theta versus X, then the area under the curve is the work done by this force. So remember that cosine theta we pick up from the dot product. The dot product is inherent in the definition for force. And so this F cosine theta can be thought of, well, it is the part of the force that's acting along the x-axis. X-axis in this case, because that's what I chose. Notice if the displacement is instead along the y-axis or the z-axis, then this would be replaced by either y or z. And the dot product can also be thought of as the projection of the force along the x-axis in this particular case, again using the x-axis as our displacement axis. We also define kinetic energy. Kinetic energy is energy of motion, and it got the symbol Ke, and kinetic energy is equal to 1/2 the object's mass times its speed squared. And we also got introduced to the work energy theorem. And the work energy theorem is a very important theorem for us. It always holds true. And that says that the net work, and the net work, remember, is the sum of the work done by each and every force acting. So if I've got 15 forces acting, then I've got 15 works to calculate and add together to come up with the net work. Work is a scalar quantity, so I will either have positive or negative signs for each and every work that I calculate, and what will dictate whether the sign is positive or negative is going to be the angle between the force and the displacement, as we talked about in previous videos. The net work, sum of work done by all forces acting, is equal to the change in the kinetic energy of an object, and this is always true, a very, very important theorem for us that we'll be using over and over again. Let's look at the units for work as we did in a previous video. So the units for work are going to be the units for force times the units for displacement. And so we've got newtons times meters. Newtons times meters is a joule. The units for kinetic energy are going to be the units we have for 1/2 mv squared. So that's going to be a kilogram times a meter squared per second squared. And if I collect the kilogram, 1 unit of the meter in the numerator, and the second squared in the denominator together, that defines a newton, and I'll have a meter left over. And that's also a joule. And of course, we expect the units of work and the units of kinetic energy to be the same for the work energy theorem to hold, and they do. So now a definition for energy. So energy is a very, very elusive substance that we don't really have an excellent handle on. The best definition, the best we can do in the scientific community for a definition of energy is that if an object has it, then that object has the ability to do work. And this is just the best that we have, okay? So energy is the ability to do work. A very important conservation law associated with energy is that energy is always conserved. However much you have of this stuff before a process is equal to the amount of this stuff that we call energy post-process. So energy is always conserved. It can move to different forms through the process, but however much you had before and however much you had after always must be the same. This is a holy grail for us, this conservation law that is applied over and over and over without fail. There are lots of different types of energy out there. There are 4 listed here, 3 of which we're really going to be focusing in on this semester, one of which we've already been introduced to. So kinetic energy, or energy of motion, is the form of energy that we've already been introduced to. Another type of energy is called potential energy, which we're going to be talking about a little bit more in this video, and then we'll be focusing in subsequent videos on this. An energy that we won't be looking at this semester, but is an important energy to think about, is rest energy. And rest energy is associated with Einstein's famed equation E equals mc squared. Because I have mass, I have energy. If I want to know my rest energy, then I simply plug in my mass in kilograms and multiply it by the speed of light squared. This is the mass energy equivalence principle. And c in this equation is the speed of light. So any object that has mass has rest energy, just simply because it has mass. And then another type of energy is heat energy. Heat energy is going to get the symbol Q, and we'll be dealing more with that later on in the semester. But these 3 energies, kinetic energy, potential energy, and heat energy, are going to be the 3 energies we're really going to be focusing in on this semester. So now coming to potential energy, PE. PE does stand for potential energy, and potential energy is always associated with a conservative field. That's not very satisfying, right? What is a conservative field? Well, a conservative field is a field whose forces act to conserve the sum of potential and kinetic energy. So this is going to be a useful concept for us if we're in a realm where we have only these conservative forces acting. And so let's take this potential and kinetic energy, the sum of those two, and give it a name. And that name's going to be mechanical energy. Mechanical energy is just going to keep track of the sum of kinetic and potential energy. Mechanical energy itself, it's not a different type of energy. It's just the sum of kinetic and potential energy. So mechanical energy is conserved when only conservative fields are doing work. What are the conservative fields that we're going to be dealing with? Well, they're elastic and or gravitational. So I have them defined over here, conservative fields. Conservative fields this semester are only going to entail gravitational and elastic fields. Next semester you'll pick up one more, and that'll be the electric field. But this semester we'll only be worrying about the gravitational field and the elastic field. These 2 are the only 2 fields that are conservative fields, and that we will be able to, if they are the only ones doing work, apply conservation of mechanical energy to. So potential energy, again, gets a symbol PE, but to distinguish the 2 different fields, we're going to use the subscript G for the gravitational field and the subscript S for the elastic field. And why S? Well, because mainly we'll be dealing with springs to represent elastic fields, and so we're going to use the subscript S for spring. So in the gravitational field, the potential energy, the energy associated with an object as it's located in a gravitational field, is going to be equal to the object's mass times the acceleration due to gravity here on planet Earth, that's 9.80 meters per second squared, times how high above or below or with respect to a reference point. And whatever you choose as your origin to measure h with respect to is nebulous. It doesn't matter as long as you adhere to that coordinate system throughout your process. In other words, all measurements need to be made with respect to that origin. And the potential energy associated with a spring, on the other hand, is going to be equal to 1/2 times k, which is known as the spring constant. It's empirically measured in a laboratory and is spring specific. 2 different springs are not going to have the same spring constant unless they're identical in every single way. So again, measured empirically, I would give it to my lab tech and ask him to measure the spring constant for me, and he would report what the spring constant is. We'll be focusing more on that in subsequent lectures. Times how far away the end of the spring is from its equilibrium position, squared. So both of these potential energies we'll be focusing in on subsequent videos, but this gives us a nice little overview of what energy is, one of the holy grails of physics, which is conservation of energy, and then conservation of mechanical energy, a special case that we can apply when we are in the realm that only elastic and or gravitational forces are doing work. And remember that whether a force does work or not depends on the angle that that force is making with respect to the displacement. When a force makes an angle of 90 degrees with respect to the displacement, then that force isn't doing any work. But if it makes any other angle, it could be doing either positive or negative work depending on whether the angle is in the first quadrant or in the second quadrant with respect to the displacement. So we will be focusing in more on these potential energies in subsequent videos. We'll see you next time.